let's look at some consequences of being full rank. So what exactly the consequences are kind of depend on whether you're of full rank because your rank is equal to the number of rows, or because your rank is equal to the number of columns. So let's look at those two situations separately. So first, let's suppose what we're going to do is come up with a lot of different conditions that are equivalent to being of full rank because your rank is equal to the number of rows. So what we're going to do here is show that some of these are equivalent. So right, I have a lot of different conditions here. What we're going to show is some of them, like condition 1 is equivalent to condition 2. We're going to show a lot of these are equivalent like this both ways. But then for some of them, it's actually going to be easier to show that, say, the third implies the fourth, and then the fourth implies the fifth, and then the fifth implies the third. Right? This still shows that they're all equivalent. It's just the proof is a little easier this way. Okay, so first let's show that your rank being equal to the number of rows is the same as the rows being linearly independent. So let's prove the implication this way first. So assume the rank is m and show that the rows are linearly independent. Well, remember that the rank is one interpretation we had for the rank is that the rank is the dimension of the row space. Well, if the dimension of the row space is m, the rows are a spanning set for the row space, right? This row space is just the span of the rows. So if your rows are a spanning set and they're linearly independent, well, there are m of them, right? So if you have, I have that backwards. If you have m rows and they span a space of dimension m, they have to be linearly independent. That's one of the facts that we proved about linear independence a while ago. So that proves the implication this way. Now let's prove the implication the other way. So suppose that our rows are linearly independent. We want to show that our rank is m. Well, what is the dimension of the row space? Well, on the one hand, the rows span this space because that's the definition of the row space. But if the rows are also linearly independent, that means the rows are a basis for this space. And that means that the dimension of the row space is the number of basis vectors, which was just the rows, because remember, our rows were serving as the basis. But that's m. And so we've shown that if your rows are linearly independent, then the dimension of the row space has to be m, but the dimension of the row space is the rank. So that shows the implication going this way. Okay, so now let's show that this is rank being m is equivalent to the nullity being n minus m. Well, remember the rank nullity theorem is true for every matrix, right? That has nothing to do with being of full rank. The rank nullity theorem says the rank of A plus the nullity of A is n. But now, if we're assuming that the rank of A is m, then we get m plus the nullity is n. But then if we just move the m to the other side, we get that the nullity is n minus m. So that proves the implication going from rank to nullity. Now let's prove it the other way around, going from nullity to rank. Well, remember, the rank nullity theorem says that the rank plus the nullity is n. But if we're assuming that the nullity is n minus m, then we get this. And now if we move this n minus m to the other side, we just get rank A equals m. And so that proves the implication going from nullity to rank. All right. Now let's show that rank being equal to m is equivalent to the column space of A being all of Rm. So remember, since each column has m entries, this column space is definitely contained in Rm, but the question is it all of Rm? Well, the rank is the dimension of the row space, but the dimension of the row space and the dimension of the column space are the same. which isn't obvious, but that's something that we proved. So the rank, which we're assuming is M, is the dimension of the column space, but the column space is contained in Rm. If you have a space of dimension m in a space of dimension m, those have to be the same. That's something that we proved when we were looking at linear independence and bases. So since we have this column space of dimension m inside a Rm, the column space has to be all of Rm, and that is what we wanted to prove. We wanted to assume that the column space is all of Rm. Okay, so we know that the rank of A is the dimension of the column space of A, but what is the column space of A? Well, we're assuming that the column space of A is all of Rm. And what's the dimension of Rm? It's m. And so the rank of A is m. All right. Great. So now, so that proves from this column space to Rm. So all of these first few conditions, we now have the implication going both ways. So now let's prove that they're all equivalent to this, that this equation is consistent. Well, let's suppose that the column space of A is all of Rm. Well, remember, so Rm is column space of A. Remember that another name for the column space of A is the image of A. And the image of A is just all the vectors that look like A times something. Well, so what we're saying here is all of Rm looks like A times something. Well, B is in Rm. And so that means that there is some x, some vector x, so that Ax equals B. But that means that this equation is consistent, and so we're done. All right, so now let's prove it the other way. Let's assume that this equation is consistent, and let's prove that the column space is all of Rm. Well, that's just the same thing, but the other way, right? If Ax equals B is consistent for every vector B, then this set is the image, right? This, by definition, this is the image of A, but this must be all of Rm. But this set is also the column space, right? The image is also the column space. So if this set is the column space, well, this set is Rm, and so that proves the implication that way. Okay, though, believe it or not, those are the easy ones. Here's the tricky one. So let's prove that if the rank, so what we're going to prove is if the rank of A is m, then we're going to show that A times A transpose is invertible. Okay, well, A is m by n, and A transpose is n by m. So that means that this product is going to be m by m, just for the record. Okay, so let's suppose that A transpose times x, some vector x is equal to 0. So who knows what this vector is? What we're going to show is that this vector has to be 0. Okay? So suppose we have some solution to this equation. Let's take this equation and multiply on the left by x transpose. Well, if we multiply both sides of this equation on the left by x transpose, we get x transpose times A transpose times x equals, well, this is a 0 vector. When you multiply the 0 vector on the left by x transpose, you get the scalar 0. Okay. Yeah, both of these are size m, here and here. Okay. But we can rewrite the left-hand side of this equation here. We can rewrite it like this. A transpose X transpose times A transpose X equals the scalar 0. Right? So remember, one property of the transpose is the transpose of a product is the product of the transposes, but the other way around. So here I'm using that property, but backwards. All right. Now, one other property that we've seen about vectors is that each of these is a vector, and one property we've seen about vectors is if you do a vector, the transpose of a vector times itself, you actually get the dot product. So this is A transpose X, right? This is a vector dotted with itself. And we're getting the scalar 0, but that means that A transpose X has to be 0. Right? The only vector that gives you 0 when you dot it with itself is the vector 0. So A transpose X has to be the 0 vector. But that means that X is in the null space of A transpose. But how big is the null space of A transpose? What is the nullity of A transpose? Well, the nullity of A transpose is it's the number of columns of A transpose, which is M, minus the rank of A transpose. Right? That's the rank nullity theorem applied to A transpose. But what's the rank of A transpose? The rank of A transpose is the rank of A. That's something we proved. But we assumed that the rank of A was M. So the nullity of A transpose is 0. That means that the dimension of the null space of A is 0. Well, here we have a vector in the null space. So X is in the null space of A transpose. But the null space of A transpose is just the 0 vector. So that means that X is the 0 vector. All right, so let's take stock. We assumed that there was some vector that when you multiplied by A transpose, you get 0. We showed that that vector itself has to be the 0 vector. This shows that the null space of A transpose is just the 0 vector, right? The only solution to this equation is the 0 vector, and that means that the nullity of A transpose is 0, so the rank of A transpose has to be equal to the number of columns, which is M. Right? But A transpose is M by M. If your rank is M by M, or if you're a square matrix of size M and your rank is M, that means that you're invertible, right? So A transpose is invertible. Okay, so finally we proved what we wanted to prove. Okay, so if you're of full rank, if your rank is M, then A transpose is invertible. Now we're going to show if A transpose is invertible, then there's a matrix B, so that A times B is the identity of size M. So this matrix B has to be N by M just for this equation even to make sense. Right? A is M by N. I'm claiming to come up with a matrix that's M by M, so B had better be N by M. Okay, and we're assuming that A transpose is invertible. Well, I'm going to play a cheap trick, which is I'm just going to tell you what B has to be. B is A transpose times the inverse of A transpose. So how do I know that this exists? Well, that's the assumption, right? We're assuming that A transpose is invertible, so this inverse has to exist. Okay, so now let's check that A times B is the identity of size M. Well, A times B is, first of all these products are defined, right? A transpose is n by m, and this inverse is, well, let's see, A is m by n, A transpose is n by n, n by m, so that product is m by m, and so its inverse is m by m. And so when you do this multiplication, you get something size n by m, which is what we said. Okay, now let's work out this product. So it's A times B, but B is A transpose times A transpose inverse. But look, here we have a matrix times its inverse. What do you get? You get the identity of the appropriate size. What is the appropriate size? Well, it's m by m, so this is the identity of size m. All right, so that proves that invertibility gives you this matrix. All right, now we have one thing left to prove, which is that this last condition implies that the rank of A is m. Or actually, what we're going to prove is this condition, that this matrix is consistent for every B. Okay, so suppose that for our matrix A, there is a matrix B so that this product is the identity. Now, we want to solve, or we want to show that AX equals B is consistent for every choice of B. In other words, we need to solve this equation, assuming that this matrix B exists. Okay, so for any B, for any vector, little b, that's equal to the identity of size m times the vector b. That's obvious. For this equation to make sense, b has to have m entries. So a vector is just the identity times the identity of the appropriate size times b. But this identity matrix, we can write this as A times capital B times little b. So now we have this vector B is A times capital B times little b. But that means that the x we were looking for is just capital B times little b. So we've shown that no matter what b is, this equation has a solution. Here is the solution. And that proves the last implication. So that connects, that sort of closes the loop of implication, and it shows that all of these conditions are equivalent. All right, well now let's do the same thing for full rank the other way. So the second flavor of being full rank is full rank because your rank is equal to the number of columns. So let's suppose that your rank is equal to the number of columns. We want to show that this means the columns of A are linearly independent. Well, this implication both ways is the same as it was for the case with rank of A being m. So the rank of A is the dimension of the column space of A, but here we have the columns are a spanning set. So if this is n, if this is the number of columns, then they must be linearly independent. If they're linearly independent, then the dimension of this space is n, in which case rank is n. So this implication goes both ways. Okay. Now let's prove that this is all equivalent to this equation, Ax equals 0, having only the trivial solution. Actually, let's do this one first. Let's do the nullity one first. So let's prove that rank n is equivalent to nullity being 0. Well, again, this is because of the rank nullity theorem. Rank nullity theorem says that rank plus nullity is equal to n. But if the nullity is n, then, I'm sorry, if the rank is n, then the nullity is 0, and we're done. But if the nullity is 0, then the rank has to be n, and so the implication goes the other way. All right, so now let's show that if the nullity is 0, then this equation has only the trivial solution. Well, remember, the nullity is the dimension of the null space. And the null space is just the vectors that get sent to 0 when you multiply by a. So this is, and so how could it be that the dimension of the null space is 0? The dimension of the null space is 0 when the null space of A is just the 0 vector. So what we need to show is that if the null space is the 0 vector, then this equation has only the trivial solution. But those two sentences mean exactly the same thing, right? The null space being the 0 vector means there's only one, means that 0 is the only solution to this equation, and vice versa. So this goes both ways. All right, next, let's show that this is all equivalent to the row space of this matrix being n. So the row space is contained in Rn because the rows have n entries. So what is the dimension of the row space? Well, the dimension of the row space, just by definition, or theorem, I guess, depending on how you look at it, the dimension of the row space is the rank, but we know that that's n. So here we have a dimension n space sitting inside Rn. That means they have to be equal. That's something that we proved a while ago. And vice versa. If Rn is equal to the row space of A, then the dimension of the row space of A is n, but that means that the rank has to be n by definition. So these go both ways. This implication goes both ways. All right, now we're going to think about A transpose A, and this is where we're going to assume that the rank is n and then show that this is invertible and then sort of make a loop of implications. So let's prove that, assuming all of these equivalent conditions up here, let's assume that A transpose A is invertible. All right, so let's suppose we have some solution to this equation. A transpose A equals the 0 vector. We're going to play the same game as we did with the other flavor of full rank. Multiply this equation on the left by X transpose. We get X transpose A transpose A X equals 0. But now we can rewrite this as AX transpose times AX equals 0. And now remember, this 0 is the scalar 0. This tells us that the dot product of AX with itself is 0. But that means that AX has to be 0. But remember, we're assuming all of these equivalent conditions, or we're assuming one of them, which implies all the others. So in particular, the nullity of A is 0. Right? But that means that the null space is empty. So, or not empty, but the null space is only the 0 vector. So that means that X equals 0 is, the vector 0, is the only solution. Okay, so the nullity of A transpose A has to be 0. But we've seen before that if you have a square matrix whose nullity is 0, that means that the matrix is invertible. So A transpose is invertible. All right. Now, assuming that A transpose is invertible, let's prove that there's a matrix B that's n by m, so that when you multiply on the left, you get the identity of size n. So B has to be of this size just for this equation even to make sense. And as before, I'm going to cheat and just tell you what B is. B is the matrix A transpose A inverse times A transpose. So this, if you check the size of this thing, it has the correct size. So let's just check what is B times A. B times A it's supposed to be the identity of size n, let's check that it is. So this is A transpose A inverse times A transpose. That all is B. Now times A. Well, here we have a matrix times its own inverse. That gives us the identity of the appropriate size. And if you check on the sizes, you'll see that this is size n. All right, so that gives us this implication. Now we have one implication left. We have to assume this, that there's a matrix B so that BA is the identity, and we have to imply one of the equivalent conditions up above. Okay, and what we're going to do is imply this one, that this equation has only the trivial solution. So let's suppose that AX equals 0, or suppose that we have some solution to this equation. Multiply on the left by B. We're assuming there is such a B. We get B times A times X equals B times 0. But on the left, B times A is the identity. On the right, B times 0 is 0. And the identity times X is just X. So here we've proven that X equals 0 is the only solution to this equation, and that closes up this loop of implications. So, right, because we have proved this. So now we have all of these conditions imply this one, which implies this one, which imply all of those up there. And so we're done.